Most people are comfortable with the idea that matter is made of atoms, and that atoms contain electrons that can move around. In solids, especially in semiconductors, electrons occupy energy bands, the valence band, which is usually filled, and the conduction band, which is usually empty. The gap between them is what gives semiconductors their special role in modern technology. Now imagine shining light on such a material. A photon can kick an electron out of the valence band and up into the conduction band, leaving behind a vacancy in the valence band. That vacancy behaves like a particle in its own right, a hole carrying a positive charge. The electron and the hole are opposites, and as with any two oppositely charged objects, they are attracted to each other. Instead of drifting apart, they can bind together in a delicate orbit, like a hydrogen atom shrunk down inside the crystal. This bound state of electron and hole is called an exciton. Excitons are subtle things. They are not particles in the usual sense. You cannot hold an exciton in your hand, but they behave like particles inside the material. Because they are electrically neutral overall, they move differently than electrons or holes alone. And because they are made of two fermions bound together, excitons often behave like bosons, meaning they can pile into the same quantum state and exhibit collective phenomena. This makes them central to a variety of frontier technologies: light-emitting devices, solar cells, lasers, and even proposals for quantum information systems. In most textbooks, excitons are presented as a relatively straightforward concept. Electron plus hole equals exciton, but in strongly correlated systems, especially under the extreme conditions of the fractional quantum Hall effect, excitons take on a far richer form. Their constituents are not ordinary electrons and holes, but fractionally charged quasiparticles that emerge from a sea of entangled electrons. When these fractionalized objects pair up, the excitons that result are no longer just neutral bosons. They can obey new kinds of statistics, form new phases of matter, and give us glimpses into physics beyond the standard categories of particle behavior. With that foundation in mind, we can now step into the triadic logic of excitons, first in their ordinary form, then in their fractional form, and finally, in the exotic phases that have just been observed experimentally. When we first introduce excitons, we normally start with the picture of an electron that has been excited from the valence band into the conduction band of a semiconductor. The absence it leaves behind is called a hole. Because the electron carries negative charge and the hole behaves effectively like a positive charge, the two are drawn together by Coulomb attraction. When they bind, they form a composite object known as an exciton. If we think about this process in triadic terms, it is essentially causal and linear. The presence of an excited electron guarantees the existence of a hole in the valence band. That hole, in turn, enables the formation of an exciton, the bound pair. And crucially, if there is no electron to excite in the first place, no exciton can ever form. In other words, electron, hole, and exciton line up in a straightforward chain of cause and effect. This is why standard excitons are usually described as bosonic quasiparticles. When you put two fermions together, the resulting composite often behaves like a boson, allowing for collective phenomena such as condensation. This linear causal picture provides the baseline for what comes next. Now we step into the fractional quantum Hall effect, FQHE regime, which is very different from ordinary semiconductors. Here, electrons in two-dimensional layers subjected to extreme magnetic fields and low temperatures do not behave independently. Instead, they form strongly correlated states in which the excitations themselves carry only a fraction of the electron's charge. These are the fractional quasiparticles, and they provide the building blocks for what we call fractional excitons. In this context, the relationship among the constituents is no longer a simple one-way causal chain. Instead, the electron-type quasiparticle and the hole-type quasiparticle imply one another because of the way fractionalization conserves charge. Their existence together supports the formation of a fractional exciton, which itself acts as evidence that the fractional constituents are present. In other words, the three elements, fractional electron, fractional hole, and fractional exciton, form a reinforcing loop rather than a linear chain. Each one depends on and points back to the others, reflecting the deep interdependence of excitations in a correlated quantum fluid. The harmony of this system becomes clear when we think about it this way. If we know the fractional electron and the fractional hole are present, then the exciton is guaranteed. If we know the exciton exists, then both fractional charges must be there to sustain it. Any two pieces of information determine the third. This is not just additive binding, it is a harmonic relationship enforced by topological order and entanglement. Finally, the mapping from fractional charges to a neutral fractional exciton is not linear. The exciton is not simply one particle plus another, but rather an emergent collective state of the whole quantum Hall fluid. The dependencies among electron, hole, and exciton are nonlinear transformations of the underlying many-body system, highlighting the difference between ordinary excitons and their fractional counterparts. Experiments in bilayer graphene have now revealed two distinct phases built from fractional excitons. The first is a fractional analog of the well-known Exciton condensate that appears at total filling factor 1. In this phase, the fractional quasiparticles bind into neutral excitons, and those excitons collectively condense into a coherent macroscopic state. The coherence of the system, the excitonic transport behavior, and the fractional composition are inseparable. They sustain one another. If coherence is present, excitons are condensed. If excitons condense, coherence must be present. And if fractional charges bind, both coherence and excitonic transport follow. Each part of the triad enforces the others, creating a convergent structure that defines this novel condensate. The second phase is more unusual. In this regime, excitons are observed that do not obey Bosonic statistics at all. Instead, their behavior falls outside the standard boson-fermion dichotomy, hinting at anyonic or otherwise intermediate statistics. Here, the fractional hole seems to serve as a junction, tying together both the fractional electron and the exciton. The three are so correlated that you cannot meaningfully separate them. If the hole is present, then the electron and the exciton are necessarily involved, and vice versa. This reflects a new kind of conjoined relationship, where the excitonic object is no longer just a bosonic composite, but part of a deeply entangled triad of fractionalized entities. This phase therefore challenges the standard picture of excitons, and extends our understanding of possible quasi-particle statistics. The presence of these exotic phases is not merely theoretical, it is seen in carefully designed experiments. In bilayer graphene samples shaped into Corbino rings, researchers measure transport in different configurations. In parallel flow, where currents run in the same direction in both layers, the system looks insulating, but in counterflow, where currents run in opposite directions, it becomes conducting. Even more striking, when current is driven through one layer, the other layer exhibits a nearly identical current, a perfect drag effect. These three observations, counterflow conduction, perfect drag, and interlayer coherence, form another triadic system. Whenever one of these signatures is present, the others accompany it. Their mutual reinforcement provides strong evidence that excitonic order is present. Conversely, when temperature rises or voltage bias increases, coherence is lost, and all three signatures collapse together. This makes the experimental detection of fractional excitons itself a triadic phenomenon. Finally, the choice of phase can be controlled by external parameters, such as displacement fields, which change the balance between layers. Adjusting this knob determines whether the system favors interlayer coherent fractional excitons, or instead settles into a single-layer polarized fractional quantum Hall state. Composition, coherence, and observed phase are tightly coupled. This means that by tuning one control parameter, the experimenters shift the entire triadic balance of the system. If we step back, we see a clear narrative progression. Ordinary excitons are governed by a linear causal triad. Electron produces hole, hole enables exciton, and no electron means no exciton. In the fractional regime, this linearity is replaced by cyclic reinforcement, harmonic determination, and nonlinear emergence. Out of that enriched structure come two phases: a convergent condensed phase in which fractional excitons collectively reinforce one another, and a conjoined non-bosonic phase that breaks away from the standard statistical framework. The experimental evidence itself forms triads of mutually reinforcing signatures, and the external controls close the loop by allowing experimenters to move the system from one triadic structure to another. In this way, Fractional excitons represent not just a new quasiparticle, but a new mode of organization. A shift from linear cause and effect to a web of interdependent triadic relationships where constituents, composites, statistics, measurements, and controls all mutually constrain one another. Excitons begin as a simple, almost textbook story, an electron promoted, a hole left behind, and the two binding together in a neutral state. This is the logic of causality, a linear chain where one step follows from the next, and the resulting quasiparticle can be treated as bosonic. But in the fractional quantum Hall regime, this familiar logic breaks down. The exciton is no longer just an additive composite. It emerges from a sea of fractionalized charges, each constituent existing only through its relation to the others. The triad shifts from causal to cyclic, each element sustaining and proving the presence of the others. From there, entirely new structures appear. In one phase, fractional excitons condense, their coherence and transport properties converging in a system where excitonic order and fractional binding reinforce one another. This is a convergent logic, where the whole is inseparable from the mutual reinforcement of its parts. In another phase, excitons no longer obey bosonic statistics at all. Here, the whole, electron, and exciton are conjoined, bound so tightly in correlation that none can be defined without the others. This is a deeper departure, a logic that escapes the binary of boson and fermion, suggesting new forms of statistics rooted in entanglement itself. The story of fractional excitons, then, is not just about a new quasiparticle. It is about how quantum matter can obey different modes of logic altogether, from linear causality to cyclic reinforcement, from convergent condensation to conjoined non-bosonic states. The triadic framework makes visible the hidden structures that govern these phases. Fractional excitons reveal a quantum landscape where what matters is not the identity of particles alone, but the logics of relation that bind them.